Hello physics students, this is Dr. Brinzy here, and this is the fourth in a series of 5 videos on Newton's second law and forces. In this fourth video we're going to look over a system that involves a pulley, and in this case we have two masses that are connected by a rope which passes over a massless, frictionless pulley. Those are important words to recognize. They affect the physics problem, and I'll tell you why in a little bit, but recognize that we need to look for these three words in order to make some certain assumptions in order to solve this problem. When we release these two masses, it's asking us what is the acceleration of the 4 kilogram mass. Okay. So just to kind of go over our series of steps that we take in order to solve problems involving Newton's second law and forces. First of all, you want to draw a sketch if one's not provided to you. And then we want to create a free body diagram. And then we want to place the positive y-axis along the normal force. Then we want to break down our vectors into components along x and y. And finally we get to write Newton's second law, and then we are going to solve to find what we need. Let's start off with a sketch here. I've already begun with the pulley and the masses, but one thing I want to show you, let's actually draw the forces on here. So we actually have gravitational force pulling this one down. And that gravitational force is -4 times g. And this one is being pulled down by -1 times g. And the other thing that I want to draw on my sketch is I want to draw which direction each mass will accelerate in. So if I imagine releasing these masses, the heavier mass will win. So this will be the one that accelerates downward. That's the heavier mass. And this one will accelerate upward because it is the lighter mass. Now, one way that we can treat this pulley system is, let me actually finish drawing this and include so I actually did a calculation of what these numbers are, just for your reference. And what we can do with this pulley system is we can actually treat it as though this entire thing were sitting on a table. So I could actually take this rope and I could move this mass over to the left and move up and to the left like that, put this one up and to the right, and so we could make something that's horizontal like this. Okay. So what I've done is I've taken the pulley out and then stretched this horizontally, so made this rope horizontal. Okay. And then what I have acting on the end of the rope here is this same gravitational force right here that's acting toward the left, and then we have a force here acting toward the right. Now the thing is that now that I've stretched this out horizontally, this force is going to become positive 9.8 instead of negative 9.8. And now we have a system that is completely in the horizontal direction, and it will behave just like this system will. Now another trick that we can do is that because this is a massless, frictionless pulley, what that does is that means that this mass is going to accelerate downward at the same rate this mass is going to accelerate upward. In our horizontal system, what that means is that these masses are going to accelerate at the same rate and in the same direction. So both of these will effectively be accelerating toward the left, like that. So now both of these will be accelerating toward the left at a rate of what I'm calling negative a. Now that's important because now we can do another little trick, and that is that we can treat this entire thing that I'm putting in dashes, in this dashed box, we can treat this entire thing like a single mass. It's going to behave as though it were a single 5 kilogram mass. So I just added the two masses together, and it will behave like a single mass that's being pulled to the left by this force. Something happened to my arrow. There it is. It'll be pulled to the left by this force. It'll be pulled to the right by that force. Okay? And it's going to be accelerating to the left. At a rate of -a. Well, that's certainly a lot simpler system than this one is over here. So we've created an equivalent system that will behave the same way that this system will. But this one's much simpler because now we just have one version of Newton's second law to write. And I wrote over this -a thing here, so let me erase that -a. Boop. There we go, make that clearer. Okay, so I have net force equals mass times acceleration. And since I'm dealing with just one dimension, I can substitute in these two masses, or two forces, excuse me, and then solve to find the acceleration. And it turns out the acceleration of this block will be -5.88 meters per square second. So this will accelerate to the left by that rate, which means each of these will accelerate to the left by the same rate. And now if I put them back on the pulley, that means this one's going to accelerate down, and this one's going to accelerate up. So this mass over here, whoops, sorry about that, I jumped ahead for some reason. I accidentally hit a button. So this will accelerate down at -5.88 meters per squared second. And this block will accelerate up by 5.88 meters per square second. Okay, now the thing about taking this shortcut is that very often the very next question you'll be asked after you find the acceleration is, what is the tension in the rope? So let me show you how you can find the tension in the rope between the two masses. So now what we can do is now we can consider just one of the masses, and I can pick either one. It doesn't matter which mass I pick. I'm going to, oops, forgot my accelerations there. I'm going to pick the 1 kilogram mass here. So I'm going to look only at that 1 kilogram mass now. And then I'm going to I'm going to create a free body diagram for that 1 kilogram mass. So the forces that are acting on it are the tension force from the rope and the gravitational force pulling it down. Well, this is a pretty easy one-dimensional problem. So I can write Newton's second law. I don't have to worry about steps 3 and 4. I can just go right to Newton's second law and write F net equals ma. And F net is the tension force minus 9.8. And, oops, let me back up there. Sorry about that. What we also know is that it's accelerating up at a rate of 5.88 meters per square second. And that's why I filled that in here, because we found that out on the previous page there. So now I have something that I can solve for tension force. Add 9.8 to both sides and add those two numbers together and you get 15.68 newtons. So that's how you'd find the tension in the rope as well. Alright, I hope this is a helpful video, especially to those of you who have been frustrated by pulleys and tension forces, and I look forward to seeing you soon. Bye.